Let's start by solving this very nice question. First of all, let's understand the geometry. What's the geometry? I think that's a pretty well drawn three-dimensional figure. I have a strip, so it's not going to be an infinitely thin wire, but rather a strip of thickness d that's carrying my current. Okay, and it's on the xy plane, going from y equals minus d over 2 to y equals plus d over 2. Current is carried uniformly along the x direction. Find the magnetic field at point P. Okay. First, let's try to figure out the direction of the magnetic field. Okay. And how am I going to do this? It's hard to draw on a three-dimensional figure. So let me look at the system from the side. Now, let's get some better colors here. So this is my z-axis. This is my y-axis. And I'm looking at from plus x infinity towards the origin. What would I see? The current is coming to me from minus d over 2 to d over 2. Now, if I take a small section here, I have a current here at a height z. Which way is the magnetic field pointing? This is a wire. There is a wire here, small wire, coming towards me. So it's going to create a magnetic field that's circling counterclockwise, which means the magnetic field it's going to create will be perpendicular to this dotted line, right? Good. So let's draw that. So the magnetic field due to that will be something like this, if this is I1. Now, if I actually just look at the symmetric piece, just on the opposite side of the y-axis, if I take another small section which has current coming towards me, oops, which way will the current create? Which way will be the magnetic field created by this current? Let's see. Again, I put my thumb along the wire, so this is going to create a counterclockwise circulating current, magnetic field. So it's going to be perpendicular to the blue line, right? Now, the magnitude of these vectors, B1 and B2, are going to be the same. Why? Because they are equidistant from my observation point. What does that mean? If I look at the components, the z components will cancel each other, while the y components actually strengthen each other. All right? I can, without giving all this argument, I could maybe just say, by symmetry, B is B magnitude minus J hat. But it's good to think about this argument. And maybe a simpler way would be the following. What would happen if D was 0? If D was going to 0? All this strip going down to a single wire. I would put my hand onto the origin, and I would exactly find the magnetic field which is in the negative y direction. Okay, that would also be an easy way to think about it. All right? Good. Now, what will my okay, finding the direction was easy. Let's actually find the magnitude of the magnetic field. And for that, here's what I'll do. if I look at the system from the top, what do I see? This is my x-axis, this is my y-axis, and here is my strip from d over 2 to minus d over 2. And as the question suggests, I'm not going to try to calculate all the strip's magnetic field at once. Instead, what I'll do is I'll think of it as if it's made up of wires, right? So I will basically think of a wire that is carrying current which has a thickness dy, and it's carrying current di in the x direction, right? Now, let me redraw the side view also. So here is my system from minus d over 2 to d over 2, and here is my y, and here is my current di coming towards me, right? If this is the y-axis and this is the z-axis. Now, can you tell me the amount of the current carried here? Di in the small section. I over d would be give me the current density. So if I multiply it by dy, I'm sorry, that's exactly what I'm just doing proportionality. If the full strip is carrying a current I, a smaller part, so dy over L times I is just going to give me the correct current carried by the small wire. But I need one more piece of information. If I have a wire here, what's the magnetic field created by this single wire? Let's try to remember that. Maybe I'll do it before everything, right? What is the magnetic field created by a single wire carrying a current I at a distance r? That's a very easy question because we can use Ampere's law to calculate it. I would say integral B dot dl is mu 0 times I in. This is mu 0 I clearly. B dot dl, B is parallel to dl, so it's just going to be 2 pi r times B magnitude. For a single wire, B magnitude at r away is apparently mu 0 I divided by 2 pi. I don't know what I'm doing. 2 pi r. Okay, so that is a result I can actually use here. But let's figure out so here is my observation point. And this angle is 90 degrees. Which component of magnetic field do I need? The y component of the magnetic field do I need. So let's actually calculate that. Now, by Biot-Savart law, the small magnetic field created by the small current is going to be mu 0 over 4 pi di. What was the next part? Good. But do I need to write Biot-Savart law? Why are you? No, I don't need Biot-Savart law. Why? Because I have already calculated the field of a line, of the wire. What I actually need to use is not that, but the formula here. Mu 0 over 2 pi r. Mu 0 over 2 pi. But what's r here? What's the distance from the current to the observation point, you're right, this is not Z, this is called H, right?
H to the 2 plus 1.
H square plus Y square, square root of H square plus Y square. Good. And how about I? I is just di, right? But that's the magnitude of the B field. I don't need that. I actually need to find out if this angle is alpha. I need to find out cosine of that angle, right? If that angle is alpha, what's the angle here? It's alpha again, right? This is 90 minus alpha, so it's alpha again. So what's cosine alpha? Cosine alpha is H over square root of H square plus Y square. Excellent. So let me call this dBy. It's going to be mu 0 over 2 pi di divided by H square plus Y square times cosine alpha with a minus sign for direction. So dBy would be minus mu 0 over 2 pi H divided by H square plus Y square and di we have just said is I over L times dy. Where is the minus sign coming from? Because my y component is towards negative y axis. That's why I wrote it down. Okay? So how do I find by? I have to integrate dby. Okay. Let's write all the constants out. Mu 0 h I over 2 pi L integral 1 over H square plus Y square dy. What are the limits of my integration? Minus d over 2 to d over 2. Why? Well, if I look at my strip, I'll start from minus d over 2 and I'll go to d over 2. Okay. So if you you're at this stage, if you correctly found the integral, that's 9/10 of your grade. Okay. But if you can actually evaluate this integral, it's even better. Can we evaluate this integral? How do we do that? By a trigonometric substitution, and it's not a very hard trigonometric substitution. Generally, this is going to be enough. This is y, this is h, this is theta, right? So tangent theta will be y over h, cosine square theta d theta will be 1 over h times dy mu 0 h over 2 pi alpha. Can you tell me what this L is? I seem to have invented something that wasn't there. L should be D, right? L is the total width of the strip, so it should be D. And here is my integral. Now what is h square plus y square? H square, okay. Cosine theta is h divided by h square plus y square square root. So h square plus y square I can write as h squared divided by cosine squared theta. Okay? So let's do that. Instead of h squared plus y squared, I'll write h squared divided by cosine squared theta. And instead of dy, I will write h times cosine squared theta, right? Times d theta. How about my integration limits? Where do they start from and where do they end at? Here I have to be careful. I must use arctangent d over 2h, and here I must have arctangent d 2h. Okay. No one is going to correct me at all. I actually have a bigger problem. I'm making a mistake really on purpose and no one is correcting me, which makes me doubt our math department. Because I took the derivative of tangent and no one said, hey, you did that wrong. What's the derivative of a tangent?
1 over.
Come on, what's the derivative of it? 1 over cosine squared theta, right? Or 1 plus tangent squared theta, which is the same thing. So this is going to be 1 over cosine squared theta. So this guy actually is not h times cosine squared theta. It's going to be h divided by cosine squared theta. Cosine squared theta is cancelled. H is cancelled. Mu 0 I over 2 pi d. And the integral becomes the simplest integral in the world, right? So overall, that just gives me 2 times arctangent d over 2h. So apparently, B magnitude is mu 0 I over 2 pi d times 2 arctangent d over 2h. Okay? Now you're glad it was a bonus quiz. But let's check. First of all, let's check the units. Or first, let's check if I reached my goal. Did I reach my goal? Is everything expressed in terms of given quantities? Yes. But what did I do? I did something wrong in the middle. In the middle, I invented some quantity called L. And after a while, I realized that there was no such quantity. Please keep checking that you're actually writing the correct symbols. Many times when I'm grading a paper, I see new symbols being invented. So be careful about that. So I reached my goal. How about the units? And it's not too hard. Why? Because I know that the unit for mu 0 I over 2 pi d is Tesla. And here, whatever is inside the arctangent should have no units. D over 2h has no units. That's good. But there is actually a very nice limit here. Limit d goes to 0. What happens when I squeeze this strip into a single line? I should get back the wire, right? That's it. So let's see. Mu 0 I over 2 pi d 2 times arctangent d over h. But if I blindly take the limit, both the numerator and the denominator go to 0, right? So I must do this limit carefully. How can I do that? L'Hopital, that's one way to do it, but I don't think you guys remember the derivative of an arctangent. You don't even remember the derivative of the tangent. So that's not a bad joke. Come on. Now, here's the nice thing. Let me teach you a nice way to do such limits. If you don't remember, it's possible that you don't remember the derivative of arctangent, but what you would remember is that tangent theta is sine theta divided by cosine theta. And if theta is very small, tangent theta, for sine theta I can say it's theta. For cosine theta, it's almost 1, right? So for small angles, arctangent theta is almost theta. Now, if d is going to almost 0, this whole expression is mu 0 I over 2 pi d times, instead of arctangent d over 2h, I'll just write d over 2h. If d is going to 0, that expression should be valid. It's for small d. So now these cancel, 2's cancel. The result I get is mu 0 I over 2 pi h. Exactly what I would expect if there is only a very narrow wire that's carrying all my current. So once I actually get the same result for the wire, I'm pretty sure I actually found the correct result. All right? My units check, my limits check, so everything is very nice. Any questions? This could very well be on the exam. So if you're feeling uncomfortable solving with the solution, you should study very hard for the next 4 days. All right? Try to solve as many of the suggested problems as possible. Question?
For d infinity, it gives for the plane.
For d infinity, that's an excellent question. For the d infinity thing, it gives me the result for the plane, because what happens when...
Pi over
Yes, exactly. So it becomes pi over 2 and I get exactly that limit. Good. Let me solve one more question. How did I do that? That's amazing. Every time the computer updates itself, there are some new tricks I have to learn. Now, let's talk about wire loops. Let's do this A. So a wire is bent into this strange shape. Wire is bent into two semicircles of radius A and B as shown. Find the magnetic field at the center. So basically this point, if the loop carries a current I. Let's say this is part A, part B. Find the magnetic moment of the loop. Is the geometry clear? I take a wire and bend it into this strange shape. Okay. Maybe I should draw these radius vectors with other colors. So here is radius A and here is radius B. And the current is I. How do I do that? Clearly, I mean, there isn't enough symmetry to use Ampere's law. So we're reduced to using Biot-Savart law. But now, my loop has 4 sections. The upper semicircle, these straight sections, and the lower semicircle. So what do I need to do? I need to calculate each one of them contribution separately. And then, because magnetic field can be calculated by superposition, just add up the vectors I find. So here is our strategy. Calculate the contribution of each section. But maybe it's not too bad. Let's look at straight parts. So here is my wire, and I'd like to calculate the magnetic field at point P. What's the magnetic field created by this straight wire at point P? Okay, it's 0, but why? Well, let's remember Biot-Savart's law. If I take a small section here, here is my dl. How about my radius vector? It's going to be this, r. So Biot-Savart law tells me that dB is mu0 I over 4 pi times dl cross r hat divided by r square. But on this straight section of the wire, dl is parallel to r. So dl cross r hat is 0. So both of these straight sections do not contribute any magnetic field. Another way to think about it is, if I have a wire here, I know what the magnetic field looks like. It circles with this right-hand sense. So what's the magnetic field exactly in the direction of the wire? It should be 0, because circulation is around that point. By symmetry, it should be 0. Okay? So the two straight parts of my loop do not contribute at all to my magnetic field at the center. So contributions from 2 and 3 are 0. Then what do I need to do? I need to find the contribution from 1 and 4. Are they creating magnetic field in the same direction or opposite direction? How many of you say it's the same direction? How many of you say it's the opposite direction? Why are you so... half of the class did not have an opinion. That's the worst possible case. Come on. We had two kinds of right-hand rules. One right-hand rule was very simple. It told me if I have a loop of wire, I put my 4 fingers along the current direction, I'll find the magnetic field with my thumb. All the current is rotating counterclockwise here, which means the magnetic field is towards me at that center. It doesn't change whether I'm coming from the top of the wire, top of the loop, or the bottom of the loop. What was the other right-hand rule? It was that if I put my thumb along the current, my 4 fingers tells me the sense of the rotation of the magnetic field lines. So if I put my on the top section, my magnetic field is coming out. If I put my finger at the bottom section, again it gives me a magnetic field that's coming out. So they are in the same direction. Good. Then let's actually calculate the magnetic field created by a semicircle. That's it. Semicircle creating a magnetic field. So I would like to calculate the magnetic field at point P. I'll take a section at angle theta. It will be a small section which has thickness d theta. So that will be my dl, and that will be my radius vector. Let's see what dB is. The direction we have just said is towards me. Okay, I won't have to calculate it, so I'm just going to look at the magnitude. Mu 0 I over 4 pi times dl cross r hat magnitude. I need dl magnitude. What's the r hat magnitude? Well, it's whatever the radius is. No, r hat magnitude is always 1. Good. How about the angle between r and dl? 90 degrees. So sine of 90 degrees is 1. So this is going to be dl over r square. How about dl magnitude? What's dl magnitude? It's the length here. It's r d theta. So dB magnitude is mu 0 I over 4 pi r d theta divided by r square. Then what's the magnetic field magnitude created by a semicircle? Clearly it's mu 0 I over 4 pi r. I have to integrate d theta from 0 all the way to pi, which will be mu 0 I over 2 pi, 2r. 4r, excellent. Now, do I have one semicircle in this figure? Oh, I have two semicircles which are creating magnetic fields in the same direction. So I will say B. First, let me give the direction is coming towards me. That's what I established. And magnitude of B, I'll have two contributions. From the upper semicircle, I will have mu 0 I over 4 B, and I'll have another contribution, mu 0 I over 4 A. Okay, so mu 0 I over 4 A plus B divided by AB is my answer. All right? Any questions? No? Okay, so here's the thing. I originally planned that I will actually solve more examples today, and then on Wednesday I'll do a review of what we have learned. But then I checked what we'll do after the exam, and the schedule is very, very busy. Okay, in the remaining 3 weeks we'll have to cover a lot of chapters. So what I'll do is I'll do a review in the second hour today, and on Wednesday I'll start talking about induction. Right? But in the meantime, if you have questions that I think I should solve, you can email them to me. Okay. Maybe I'll take over the recitation hour. I don't know yet. Okay. But try to look at your book. Try to ask me questions. We have only 4 days left until the exam. Okay. So in the second hour, we'll do a review for the exam. All right.